Welcome. I'd like to reintroduce you to quant unknowns analysis focusing on accurate mass. So this is the seamless integration of quantitation and moving into unknowns analysis. The basic purpose here is to find tentatively identified compounds, sometimes called non-target analysis. And those compounds could include degradation products, contaminants, even impure standards. So if we look at the workflow, you can see that we run through the regular quantitation. We have targets, final concentrations. After we finish that with this scan data, either unit mass as discussed previously or now accurate mass, the unknowns will then apply deconvolution to create a list of components. Those components will be matched with a spectral library, and some components will match up and be promoted to hits. Now the hits then fall into two big bins. The first is if they match up with previously identified targets according to the criteria, they will end up target matched and be classified as target hits. Those which you're interested in now, which you have not seen, are the non-target hits. And after you've reviewed those in the unknowns presentation, you can then promote those to what I'll call tentatively identified compounds. A couple important points in comparing unknowns analysis is the fact that unknowns uses a different technique. Quantitation, of course, extracts, producing an extracted ion chromatogram, and you see the spectra from the averaged. In unknowns, we're using a technique called deconvolution, which in brief finds the ions that elute together in a model peak shape and groups those together into a component. And as you can see here, we have a library of spectra that we've collected, and it's going to match up against that spectra, giving you a library match score. So that's an important distinction between extraction of ions and then deconvolution and library searching. So here we are looking at quantitation that we know and love, and moving on to quantitation. It's worth mentioning as an overview that we have a new TOF data access layer, which speeds up the quant analysis by a factor of 5. Also, on the unknowns end, we, as you can see, have a presentation here, and you'll experience a performance improvement of about 50 times because the extraction of the chromatogram is the main job that needs to be done with deconvolution, and that's what the data access layer organizes your data in a new format on your disk. So it speeds up chromatographic extraction. Let me breach the topic of the difference between unit mass and accurate mass. So the first is, well, accurate mass instrument like a TOF is not really a scanning instrument. You might call that full scan or faster spectral acquisition speed. But the result of that is more points across the peak. So that's going to lead to better integration, or in deconvolution, the more points across that model peak shape that you're looking for would lead to better resolution of those components. Now the same argument is applied here in terms of sensitivity. In the MSD, the scanning is not spending that much time on any particular ion, whereas in TOF the ions are all accelerated in a pulse, so you might end up with better sensitivity there in terms of the ions seen. Another argument in favor of the time of flight is that if you have two masses that are very close together, but the resolution of the TOF allows you to separate them by narrowing the extraction window, you could reduce that interference or eliminate that interference in quantitation, and even in deconvolution see that as a separate ion because of the inherent resolution of the time of flight. Now on the other side of the coin, let's discuss saturation very briefly. From a dynamic range point of view in quantitation, saturation is going to affect you on the high end. At a certain point, that detector will not be able to go beyond that because the ion that you're monitoring turns out to be saturation effects. And the same goes for deconvolution. Some ions could be affected, which could lead to a deleterious effect on your score. All right, let's step into the question of the difference between unit mass and accurate mass machines like a time of flight. So the first thing is that a time of flight is not really a scanning instrument. You might call that full scan. But the difference is that the faster acquisition speed versus, let's say, the MSD makes a significant difference in terms of your quantitation. And it's easy to understand because that would end up giving you more points across the peak, which would lead to better integration. And in unknowns, when you're trying to do deconvolution and separate peaks by retention time into these model peak shapes, the finer granularity of more points in retention time space would give you better resolution. So that benefits both quant and unknowns analysis. And the sensitivity argument is not very different. MSD is scanning, not spending a lot of time on any particular ion, where TOF has an advantage that it pulses all the ions together that are there with the potential of better sensitivity. Now, definitely an advantage of accurate mass is the fact that if you've got masses that are close together, one being an interference and one being the target that you're interested in, you could reduce that interference or potentially eliminate that by narrowing down the extraction window in a way that unit mass really can't do, therefore getting quantitation on your target, reducing interferences. And the last thing on the other side of the coin that I'd like to mention is saturation. So saturation is going to limit your dynamic range and quantitation. At a certain point, the detector is going to end up limited. That's an effect you need to be aware of. And certainly in unknowns, the ions could end up in a saturated condition and therefore affect your scores. Let's breach the topic of EI versus CI and its effect on quantitation and unknowns analysis. So the first point is, generally speaking, in GCMS we're dealing with EI. So we do not have a strong molecular ion. So now we have to, in quant, figure out the strong fragment ion. Now we typically do that empirically, but if you want to have the exact calculated mass, you're going to have to figure out that fragment and get the exact calculated mass. So that's some work to be done there. Another point to be made is that unlike LC, which is blessed often with a molecular ion and the adducts that you can predict, with the formula you can't really predict the molecular ion species unless you're in a soft ionization technique like chemical ionization. So that lack of formula and the ability to predict the pattern cleanly is a challenge for the EI side of the fence. So last, a comment about spectral library searching. You can certainly search the abundant libraries that we have with an accurate mass spectra against a unit mass spectra, and that works reasonably well. What is more interesting is to search an accurate mass spectra against an accurate mass library. Now, in order to create that accurate mass library with fragmentation spectra, you want to end up with the fragments again as exact calculated masses. Thanks for your attention.